Okay, welcome back everybody. So this is our second lecture in this Wells hydraulics course. This lecture is a bit of an off-topic one, so it's about radial coordinates. So it's more of a mathematical derivation of radial coordinates, so it's not really directly linked to hydraulics or to wells, but I thought it was important to link back to our previous course on the groundwater cycle where we saw all the flow equations. And all the flow equations in the first course I did in mostly 1D, a little bit of 2D, two dimensions, but they were all in X and Y axis in a plane basically, or on a line for the 1D examples. For wells, obviously the problem of wells is that they're a point pumping all around, so then we have basically circles. We're dealing with circles, so it's kind of important to understand the relationship between the equations we've seen in the first course and the equations we'll use, which are the same, just in radial coordinate in this course. So some basic assumptions also that we will use throughout this course. So aquifers are typically bounded at the bottom, and again, these assumptions are listed in the Feather book in chapter 5, so you can go and refer to that if you're interested, to see what I'm talking about. But bounded at the bottom, typically horizontal formation, so there's no slope or nothing strange, so the assumptions are very limiting, if you will, but just to simplify the problems. The surfaces are horizontal, steady prior to pumping. The changes in the potentiometric surface are due to pumping. Aquifer are homogeneous and isotropic, so again, I invite you to go back to our previous course, for those definitions if you don't know them. The flow is radial toward the well, and that's where the radial coordinates are important. Water flows are horizontal mostly. Darcy's law is valid. Again, Darcy's law is a big chunk of that first course, so please go refer to that if you haven't. Wells are fully penetrating, so this is a big assumption, and we might break it a little bit at some points, but we assume that the water is pumped, throughout the aquifer just for mathematical. It's just easier for the mathematics of it, but in reality that's almost never true. So we'll discuss this assumption a little more. Pumping well have a small diameter and 100% efficiency. So again, I discussed that, but we're assuming that the well is small compared to the aquifer, obviously, and that it's completely efficient. So the well efficiency is basically a topic in and of itself that we'll discuss. But again, for the simplification of the math, we just say, well, there's no loss of efficiency, which of course is not true. Again, why the radial coordinates? You can see those couple examples like on the right-hand side here. You can see if you have a well in the middle of that. So this is a top view of an aquifer, right? You're looking down at it, or you're looking at the water table if that's an unconfined case. And you can see if there's a well in the middle, like clearly you can see that circular pattern right around the well. So everything is circular. And then again, if you look at the 3D view of this, if you will, you can really see how this is a radial coordinate problem. So let's get into it. So again, because the wells take water from everywhere, we need to convert that XY axis into basically a R axis, right? So the X and Y here needs to be converted into a R theta, or R phi in this case, an R phi axis. For our purposes, the angle won't matter because we already said the assumption that our aquifers are homogeneous and isotropic, so there's no real change with orientation, right? Whatever you pump on the left and on the right and on the front and the back is going to be typically the same if everything is isotropic. It doesn't have to be always that way, and again, go back to previous lectures to see when that wouldn't be true. But for our case, basically, we're mostly interested in the R aspect because the phi aspects will disappear. So R, if you look at this triangle, on the left-hand side here, you can see, very easily that R is just it's a Pythagorean theorem, so it's just the square root of x squared and y squared. Now, if we have that, we can easily find derivatives and replace into our flow equation. So let's do that. Oh, first, let's take a look at that, the trig circle, I call it, right? So if you have this always does this, an x and a y, right? You take a circle of diameter 1, and then the cosine is the x-axis and the sine is the y-axis, okay? So if you remember that the cosine is on the x and the sine is on the y, and then you'll be able basically to find all these, trigonometric identities where the cosine, is the you know, on the x. So here, oh, I'm sorry about that. Right, this is your cosine, and then the sine is right here. Okay, so the sine is on the y-axis, the cosine is given by the x-axis. So then it's easy to remember, you know, which side you divide, and of course this would be your hypotenuse, right? So then you can remember everything. So if you remember this trig circle, you know, you can find anything you need from trigonometry. So cos is adjacent, right, to the angle here. Okay. All right, so going back to our definition of R and how that works for the derivatives, since we have derivatives in the flow equations. So now we're interested in the derivative of R as a function of X, for example, right? And here I just give you the Mathematica answer. You can just do it by hand, but if you do dr dx, you can actually do dr dx because now you have R as a function of X. So you can crunch that derivative and find it, right? And then at the end of the day, dr dx is x over square root of x squared plus y squared. Again, for the angle, for phi, you could also do the same. As I said before, these angles, we don't really deal with them in our course. I mean, you would if you want a general expression for the flow equations, but for us, we can sort of ignore them because of the isotropic and homogeneity assumptions. Okay, so now if you write your change of head over distance, right, the hydraulic gradient that we've talked about, again, in the previous courses, that's fundamental for Darcy's law and all the flow equation. Then the dhdx, you can replace the full derivative by the partial derivative, and with the chain rule, sorry, thank you. Using the chain rule, right, you can add dr on the top and bottom here, you know, and then again for the angle on the top and bottom without loss of generality. And then if you replace all this, then you end up with your flow equation. So this is the general flow equation. Recognize the Laplace equation here in 2D, right? The d squared of h over dx squared, you know, in 2D. And then if you replace, you end up with an equation as a function of r. So this is how you go from linear coordinates to radial coordinates. Now this whole expression is in, you know, the full expression. Like I said before, you can sort of ignore this for our assumptions. And then if you replace in the Boussinesq equation, basically the complete flow equation with the unsteady term on the right-hand side, with the recharge term, you know, the source sink term, then you can see that you can just have a complete flow equation in radial coordinates. So again, this was the general introduction. So we have the tools now, right, that we can use in radial coordinates to analyze pumping wells. All right, thank you, and I'll see you in the next video.